Hi all, my name is Chukwemeka Mafo. I'm a principal materials and corrosion engineer and I work in the oil and gas industry. Today we'll be looking at the first part of different types of corrosion. And so today we'll be looking at different types of corrosion that affects the internals of the pipelines and equipment in the oil and gas industry. So we've got the CO2 corrosion, H2S corrosion, O2 corrosion, microbial influence corrosion, galvanic corrosion, flange-based corrosion, internal chloride stress corrosion cracking, weld corrosion, crevice corrosion, and finally erosional corrosion. We will look into all these types of corrosion in details. So we look at CO2 corrosion, which is also known as sweet corrosion. CO2 is an acid gas. It's one of the composition of reservoir fluid when the oil and gas or the crude oil is brought up from the ground. So this is one of the composition that comes out with the crude oil and also the gas. It dissolves into water phase and basically increases the acidity and then causes corrosion. Where does this occur? Internals, this type of corrosion would happen in internals of vessels, pipelines, and pipeworks. In system that contains CO2 where free water is present, generally affects, and this type of corrosion affects mainly carbon steel and cast iron steel. So the next type of corrosion we'll be looking is H2S corrosion, similar to CO2 corrosion. H2S dissolve in water to form an acidic aqueous electrolyte, which is highly corrosive. H2S can be found in the well fluids and is carried over into oil, gas, and water phase after separation. H2S leads to sulfide stress corrosion cracking. Sulfide stress corrosion cracking can attack both low alloy steel and also corrosion resistance material. Where does it occur? It occurs where there's SRB activities. SRBs are bacteria, and this SRB activity generates what we call hydrogen sulfide. It also can be found in systems that contain H2S, where free water is present. Internals of hydrocarbon vessels and pipework are also where this can occur. The materials that are affected are mainly carbon steel, cast iron steel, and some corrosion resistance alloy. Example, we've got Inconel 825, which is also at risk above temperatures of 432 degrees centigrade. The next corrosion we'll be looking at is the O2 corrosion, also known as oxygen corrosion. Oxygen corrosion in carbon steel can be seen as the general wall loss. So it's more or less a uniform. It's also called O2. By the way, O2 corrosion is also called uniform corrosion. So it's just seen as a general wall loss. Oxygen corrosion in stainless steel can propagate pitting due to the presence of chloride. So it's a kind of corrosion that basically can be made even worse when you have things like chloride, and also there's a high temperature as well. Where does this occur? O2 corrosion can occur on basically carbon steel materials where oxygen and water are present, and on stainless steel materials where we have oxygen, water, and chloride, where oxygen, water, and chloride are present. The next type of corrosion we're going to be looking at is the microbial influence corrosion, known as MIC. There is this notion that microbes eat metals, and that is actually false. The real truth is that microbes or bacteria produce matters, example H2S, that react with the metal and then causes the corrosion to happen or pitting to happen. MIC or microbial influence corrosion affects mainly carbon steel, and some CRA are also at risk as well. Some corrosion resistance alloys are also at risk as well. The risk there's also a high risk in dead legs and under deposits due to stagnation and deoxygenated region. These are areas where you can find this type of corrosion. Where does it occur? It occurs anywhere there's basically microbial activities and there's water and also the nutrient for the microbes to feed in. Specific areas include, obviously, as mentioned before, dead legs, where there's low flow regions, and also on the deposit. Systems where MIC can occur includes drains, firewater, diesel, separator, and pipelines. The next corrosion we're going to be looking at is a galvanic corrosion. This type of corrosion occurs between dissimilar metals in electrical contact with each other and in the presence of an conductive electrolyte. The more active metal will corrode, while the less active metal, which is also known as cathode, won't corrode. So from the picture we can it's a good example. From what I understand, the flanges are made of stainless steel, while the bolts are made of carbon steel. So as you can see, the carbon steel bolts, which are the anodes, are corroding, while the stainless steel flanges are still in good condition. So where does this type of corrosion occur? Anywhere there is dissimilar metal, so dissimilar pipe spools, screw fittings, bolts, flanges, framework and support, instrument fitting, and also pipe work and pipelines as well, where these two dissimilar metals are coupled together. The next type of corrosion we're going to look at is the flange phase corrosion. The term flange phase corrosion describes the internal process of piping and vessels that occur in the flange phase of plant components. The mechanism is similar to crevice corrosion and tends to remain basically undetected until the flange is dismantled for inspection, or when the corrosion damage progresses to the point of failure and leaks occurs. So, I mean, with flange phase is one of the most difficult type of corrosion to detect, because it happens inside the flange. So it's really difficult to see where this type of corrosion would occur. So for those people who don't know what a flange phase corrosion flange looks like and where the flange phase, I'll take you back to the previous page. So what we see here is a flange, and in between there's two plates. In between the two plates, there's a crevice. In between the flanges, there's a little crevice, and this is where water, CO2, and also, oxygen can seep in and cause what we call flange phase corrosion. So where does this this kind of corrosion occur, as I mentioned, as I explained before, the locations and item where the flange face corrosion is likely to locations where the flange face is likely to occur is, in the flanges, like I've showed you before, regardless of the orientation or material and the operating condition, they always happen. And mainly in internal orientation of the flange, that's where you see it. Seawater systems are particularly prone to flange face corrosion. The next corrosion I'm going to talk about is the internal chloride stress corrosion cracking. So for this type of corrosion, factors which influence this type of corrosion is high temperature, chloride concentration, and oxygen availability. So we need these three elements to be able for this type of corrosion to occur. The facilities, where does this kind of corrosion occur? So we're looking at facilities with austenitic stainless steel, duplex stainless steel materials. All these materials are at risk of internal chloride stress corrosion cracking. And they need these three conditions: high temperature, chloride concentration, and oxygen availability for them to be at risk. The next corrosion I'm going to be talking about is the weld corrosion. So this type of corrosion occurs when there is difference between the weld and its parent material. The weld, or the heat affected zone, becomes anode, while the parent metal becomes the cathode. So, a good example is the picture. If you look closely, you will find that the picture below shows a welded plate or a weld, and you can see the parent material, and you can see where the heat affected zone is. So from the first picture, you could see that the parent material is intact because that's the cathode, and why the welded zone is showing signs of rusting, which basically is the anode. So the welded section has become the anode, and that's the part that is becoming corroded. So another thing that could lead to weld corrosion is poor weld quality containing porous holes. Again, from the pictures, you can see that somebody has done a really bad job in welding there, and there's porous holes in it. And poor weld dimensions, such as weld roots protruding out, resulting in local turbulence flow and erosion corrosion at weld area. So, bad welding can lead to different type of things, such as bad erosional corrosion, and also, with the parts protruding, if it's not done properly, what you would see is that area becomes, if there's flow through that section, it becomes a location where there will be turbulence, and therefore leads to pitting corrosion as fluid would flow through it. Where does this type of corrosion occur? Weld corrosion basically is commonly found in oil and gas systems, such as seawater system containing CO2 and high acetic acid environments. So the next one I'm going to look at is the crevice corrosion. The mechanism for this crevice corrosion is similar to flange face corrosion. It refers to the corrosion occurring in confined space to which the access of the working fluid from the environment is limited. Mainly occurs in chloride-bearing solution in combination with crevices that is wide enough to allow penetration of solution, but narrow enough to create stagnant condition. Where does this kind of corrosion occur? Most likely to occur in seawater application. It also occurs in areas where you have gaps, contact between gaps and contacts areas between parts. Example of that is like we've got under gaskets, seals, inside cracks, space filled with deposit and other sludge pills. So to move on, so the next and the final types of corrosion that we would talk about is the erosional corrosion. Erosion corrosion is a degradation of material surface due to mechanical action, often by impinging liquid, abrasion, or particles suspended in the fast-flowing fluid. Erosion is dependent on process fluid, what the process fluid is contained, and also temperature, pressure, and particular the geometry of the pipework. Where does it occur? It occurs in areas where there is high flow velocity conditions, such as either small diameters, reduces, bends, and poor welded region, just like the previous picture I showed you about weld corrosion. This is the end of the first part of my presentation, and I hope you like it. And I hope to be posting the second part pretty soon. Thank you for listening.